In this tutorial, I will cover the definition of a mineral, the different mineral properties that we can use to identify minerals, and some details of the most common rock-forming minerals. This will lead to an exercise on identifying some samples of common minerals. A mineral is a usually crystalline substance that has a definite chemical composition. That is to say that throughout the mineral mass there is a repeated structure containing the same relative proportions of a number of different elements, such as silicon, aluminium, iron, oxygen, or carbon. The exact arrangements of atoms, and therefore the type of crystal structure that is formed, depends on the pressure and temperature at the time of formation. Certain minerals will be more or less likely to grow given any set of pressure and temperature conditions, and of course given the right composition of available elements in solution. Some minerals are then more stable than others, in that although, for example, atmospheric conditions are not the right conditions for them to form, they are resistant to being transformed into more suitable forms and so survive in weathering to be transported and deposited as sediments. Mineral crystalline structures can be divided into many different classifications. The one that makes the most sense to explain here is the different ways in which a tetrahedron of silicon and oxygen, often called silica, can be combined to create the various silicate minerals that are the majority of the major rock-forming minerals. Silica tetrahedra can occur in isolation, bonded to others through different elements, like in the mineral olivine, common in mafic igneous rocks. They can occur in rings, like in the hard mineral beryl. We will come across this mineral again. They can form either single or double chains, creating the more common minerals in mafic igneous rocks called pyroxene and amphibole. They can occur in sheets, in which group falls all the mica minerals and also all the clay minerals. And they can occur in frameworks, which are very strong structures, stronger when the amount of other elements is less, i.e. quartz, which is just silica, SiO2, than when there are other elements involved in the framework, i.e. varieties of feldspar, which is sodium, potassium or calcium aluminosilicate, AlSi3O8. Silicates are not the only minerals that are commonly observed in the rocks we were discussing. We will look at sulfides, which are metal-sulfur compounds, some sulfates, oxygenated sulfur compounds, and many carbonates, oxygenated carbon compounds. Individual minerals have unique properties that allow us to identify them. Some of these properties are visible or determined by naked eye observations, but others require microscopic analysis or advanced techniques like X-ray diffraction to make the identification. Now we will go through some of the common methods of distinguishing minerals. Density is an important factor in identifying minerals. Different minerals will have different densities, which makes them feel light or heavy when we pick them up. Unfortunately, this is one property that is very difficult to demonstrate in a video. Hardness is a different property to density. It relates to how easy it is to break or grind a crystal down to powder. To measure hardness, we use a comparative scale called the Mohs scale of hardness, where talc is the softest mineral and diamond is the hardest. Various common items like our fingernails, copper, steel and glass are also listed to help place a mineral on the scale. A lot of information is available via visual observations of the mineral. Firstly, we can start with colour. The colour of a mineral may or may not be diagnostic. What this means is that in the case of some minerals they are always the same colour, while others can vary greatly in colour. Another colour to look for is the colour of the streak. This is a powdered sample obtained by rubbing the sample across a roughened ceramic plate. Streak is often different to the primary colour, and the difference can be diagnostic of a mineral. Secondly, we can look for the crystal shape. We will not here be talking about detailed crystallography. That is a specialist subject beyond the scope of this course. However, we can identify minerals that have distinctive crystal shapes, for example cubic crystals, needle-shaped crystals, or botryoidal growth patterns. Thirdly, there is the property called cleavage. Cleavage is the planes along which a mineral naturally breaks. If you hit a mineral with a hammer, it will break, and the cleavage planes will tend to be along lines of weakness in the crystal structure itself. These are cleavage planes. Minerals may have no cleavage planes, 2 planes, 3 planes, or more. Look for the shiny flat surfaces in a mineral sample to see the cleavage planes, and also note the angles at which they intersect. Two more observations may be made with hand specimens. Some minerals react to common chemicals, and some minerals have a distinctive taste. We, however, do not recommend tasting all rock and mineral samples, as some minerals are poisonous. Apart from these hand specimen observations, we can take a thin section of a mineral and observe it under high magnification, or we can look at it in detail under a scanning electron microscope. We can determine the elemental composition of the mineral by X-ray fluorescence, and finally we can analyse it using X-ray diffraction. This method will tell us about the crystal structure itself and is a very accurate way of determining mineral type, especially for clay minerals which are too small to be visually identified. Having covered how we identify minerals, let us now look at some of the common rock-forming minerals that we might encounter in subsurface rocks and their properties. Probably the most common mineral we will encounter is quartz. Quartz is a framework silicate composed entirely of silica, SiO2. However, this framework structure does permit other elements or impurities to be included in various quantities. Therefore, quartz comes in a wide range of colours, from purple, amethyst, to yellow, citrine, to clear and white. Quartz also occurs in cryptocrystalline forms, called chalcedony and flint, where a proper structured mineral framework is not present. Quartz has no cleavage and therefore breaks with curved surfaces known as conchoidal fracture. Quartz is hard, it has a hardness of 7, and very stable, commonly surviving weathering, so it is a major constituent of clastic sedimentary rocks. Another important mineral is the feldspar group. Feldspar is an aluminosilicate with a variety of common compositions using varying quantities of potassium, K, sodium, Na, and calcium, Ca. Words you will see used to describe the different end members include albite, orthoclase, and just feldspar. All feldspars have two cleavages at right angles, but they vary in colour, with the potassium-rich feldspars tending to have pinkish colourings and the calcium-rich to have blue colourings, while sodium feldspars are commonly white. Feldspars are slightly softer than quartz with a hardness of 6. Mica is a very common group of minerals in igneous and metamorphic rocks and occurs in clastic sedimentary rocks as well. Micas are sheet silicates, which means that they have one very strong cleavage that tends to create a crystal mass with very fine sheets that can be easily pried apart. Dark micas are referred to as biotite and clear micas as muscovite. There are other colours possible in the mica group, including green and yellow. Clay minerals are also sheet silicates and are very, very small. They are so small that the individual crystals cannot be seen with the naked eye. Clays are very soft, like talc, and have a variety of crystal habits from stacks to needles to coatings, which can be seen in these scanning electron microscope images of clays which have formed within a sedimentary rock. Pyroxene is a chain aluminosilicate with a high concentration of iron and magnesium. Like amphiboles, pyroxene is a group of minerals characterized by two cleavages at right angles and very dark black to green colors in needle or elongate shaped crystals. Pyroxene is a common mineral in mafic or silica-poor igneous rocks and some metamorphic rocks. Varieties include green gem minerals like jadeite and diopside. Minerals in the group range in hardness from 5 to 7. Amphibole is a chain aluminosilicate with a high concentration of iron and magnesium. Like pyroxene, amphibole is a group of minerals characterized by two cleavages which are at 60 or 120 degrees, which enables us to distinguish these dark elongate crystals from those of pyroxene. Amphibole is found in intermediate or silica-poor compositions of igneous rocks, and the hardness ranges from 5 to 6 depending on the mineral composition. Calcite is calcium carbonate, a very important rock-forming mineral in sedimentary rocks, forming by the growth of organisms with calcareous skeletons, organic sedimentary rocks like limestone, but also forming as a cement in all sedimentary rocks. Calcite is distinguished by having three cleavages at 60 or 120 degrees to each other, forming in broken specimens little rhombic shapes. The crystals are pointed and tend to be elongate. They range in colour from pink, green, blue, white, yellow or cream depending on the impurities that are present in the crystal structure. Calcite is relatively soft with a hardness of 3 and also has the distinguishing characteristic that it reacts vigorously with dilute hydrochloric acid, forming a mass of bubbles. Another important carbonate mineral is dolomite, which is calcium magnesium carbonate, which does not react with acid and tends in outcrops from crystals to have a yellow or brown appearance. Gypsum and anhydrite are both calcium sulfate minerals. The difference is that gypsum retains some water in its crystal structure, while anhydrite is waterless. Both are formed during evaporation of salty water masses. The colour of these minerals does vary again depending on impurities that are present. Pure crystals are clear to white. Both are soft, with a hardness of 2 on the Mohs scale. Halite is another mineral that forms during evaporation of salty water. This is sodium chloride, or common rock salt. This mineral can be distinguished by taste if you are brave enough. Halite has a perfect 3 directions of cleavage at right angles, so forms cubic shapes if broken. It dissolves readily in water, has a hardness of 2.5, and can be clear to variously coloured depending on the presence of impurities. Pyrite is iron sulfide, one of the common ore minerals for iron, and known as fool's gold due to the metallic gold lustre of the crystals. The streak for pyrite is however greenish black. Pyrite crystallizes in perfect cubes with a hardness of 6 to 6.5 if conditions allow, or may grow in botryoidal or acicular forms, or as grain coats or massive tiny crystals. It does not have cleavage when broken, but the crystal shapes and the colour are diagnostic. Hematite is iron oxide and another common ore for iron extraction. Crystalline hematite is dark metallic black or grey, but a streak is always reddish in colour. It has not cleavage and a poorly developed crystal structure, commonly forming in botryoidal masses or as massive layered deposits. Depending on the type of growth and mineral structure, hematite can vary in hardness from 5 to 6.5 on the Mohs scale. Graphite is a pure carbon structure, often formed during metamorphism of carbon-rich rocks buried to sufficient depth and temperature. It has a very slippery feel due to the low hardness, 1 to 2 depending on the crystal structure, and a single cleavage with a metallic grey to black appearance. These are just some of the many minerals that occur in the real rocks, but represent a group of the most common examples that you are likely to encounter. Test your new knowledge with the exercise in identifying minerals.